Let's start this session now. At the request of the two speakers in this session, the order of the talks has been changed because it was felt that the second talk in the session, which is now the first talk, would give a good background to the problem that is covered in what is the first talk, but will now be the second talk. So the first talk in this session is by Professor Tsubota of the Department of Physics, Osaka University. He will talk about quantum turbulence from superfluid helium to atomic Bose-Einstein condensate.
Thank you very much. Can you hear? So now, first of all, I'd like to thank the organizers for inviting me this wonderful conference. I'm Makoto Tsubota, coming from Osaka City University. Today I'm talking about quantum turbulence from superfluid helium to atomic Bose-Einstein condensates. So this is the summary of my message today. Quantum turbulence has recently become one of the most important fields, especially in low temperature physics. And the quantum turbulence consists of quantized Bose-es, which are stable topological defects. Since each element is clear and well-defined, quantum turbulence is able to give a much simpler prototype than classical turbulence. Quantum turbulence has been studied in superfluid helium for more than 50 years. Since the middle of 1990s, quantum turbulence research has tended toward a new direction, now involving atomic Bose-Einstein condensates too. So this is a famous sketch about 500 years ago by Leonardo da Vinci about the turbulence. Da Vinci observed the turbulent flow in water and found that turbulence consisted of many Bose-es. So we could call this message another Da Vinci Code, because probably the name comes from the very famous popular movies and novels. Probably some of you like it. And anyway, another Da Vinci Code in my talk highlights the fact that turbulence is not a simple disordered state, but rather it consists of some structures with Bose-es. Certainly, this is a very exciting movie which shows the turbulence in the wake of a dragonfly. Please observe it carefully. Certainly, you can find some vortex-like, eddy-like structures around here. However, these Bose-es are unstable. They repeatedly appear, diffuse, and disappear. So the quantum turbulence is comprised of quantized Bose-es, which is much different from classical Bose-es. So in this view graph, I'd like to summarize the properties of quantized Bose-es. A quantized vortex has originally a vortex of inviscid superflow appearing in a Bose-Einstein condensation. And any rotational motion in superfluid is sustained by these quantized Bose-es. Quantized Bose-es has some properties much different from usual Bose-es. First, the circulation is quantized by this quantum circulation kappa. Since a vortex with a quantum number larger than 2 is unstable, actually, every vortex has exactly the same circulation. Second, this is a vortex of inviscid superflow, thus being free from the usual decay mechanism of the viscous diffusion of the vorticity. So this vortex is very stable. Thirdly, the vortex core size is found to be very small. The order of the coherence length in the case of superfluid helium-4, the vortex core size is known to be the order of the angstrom size. So on the contrary of the properties of classical turbulence I described previously, the quantum turbulence consists of a quantized Bose-es which are stable topological defects. Each vortex has the exactly same circulation, and the circulation is conserved. Therefore, we can say quantum turbulence may be much simpler than classical turbulence because each element of the turbulence is definite and clear. So we can expect that research into quantum turbulence can make a breakthrough into one of the great mysteries of nature, of course, turbulence. So the contents of my talk are as follows. First, I'd like to review very, very shortly the research history of quantum turbulence. The second part is I would like to discuss the recent quantum turbulence studies in superfluid helium. The last part is devoted to quantum turbulence in atomic Bose-Einstein condensates. Now we'd like to remember very, very shortly the research history of quantum turbulence. As you know, liquid helium-4 enters the superfluid state below 2.17 Kelvin with Bose-Einstein condensation. Its hydrodynamics are well described by the two-fluid model. The two-fluid model states that the system is a mixture of inviscid superfluid and the viscous normal fluid with a mixing ratio depending on the temperature like this. The two-fluid model can explain various experimentally observed phenomena of superfluidity, such as the thermomechanical effect, film flow, or etc. However, it has been known since the 1940s that superfluidity breaks down in fast flow. This is a sketch of the case. When the velocity is smaller than some critical value, the two fluids do not interact, so that the superfluid can flow forever in principle without decaying. However, if the velocity exceeds the critical value, a tangle of quantized velocities appears and develops. The two fluids becomes to interact through mutual friction generated by tangling, and eventually the superfluid decays. Actually, this idea was proposed by Richard Feynman in 1955, who proposed that this is a superfluid turbulent state consisting of a tangle of quantized velocities. This is a famous figure appearing in Feynman's famous article. Feynman said, in a turbulent state, such kind of large vortex loop should break up into smaller vortices, similar to the cascade process in classical turbulence. In late 50s, Joe Vine observed experimentally superfluid turbulence, thus finding mutual friction between the vortex tangle and the normal fluid causes the dissipation of the flow. After that, many experimental studies were conducted chiefly on thermal contact flow of a superfluid helium-4. This is a sketch of the case. When heat is injected into the left side, in this case, the normal fluid flows from the left to the right, and the superfluid flows oppositely, and here appears a vortex tangle causing the dissipation of the flow. In 1980s, Klaus Schwartz performed a direct numerical simulation of the three-dimensional dynamics of quantized velocities and succeeded in quantitatively explaining the temperature difference delta T between two cells from the vortex dynamics. This animation, which was made by our group, shows how initial 6 vortex rings grown up to a vortex tangle under the thermal contact flow. We used the periodic boundary condition around this direction, and the other boundaries are solid. Anyway, Schwartz obtained numerically the statistical steady state of a vortex tangle, which is sustained by the competition between the excitation due to the applied flow and the dissipation due to the mutual friction. The calculated vortex density L agreed quantitatively with some typical experimental data. Certainly, this was a great success of the numerical research. However, most studies of superfluid turbulence have focused on thermal contact flow, which has no analogy with classical turbulence. For example, Richard Feynman drew this figure. He was thinking of a cascade process in classical turbulence. Then there remains a very important question. What is the relation between superfluid turbulence and classical turbulence? How can we study the similarities or difference between QT and CT? Probably as a strategy, one of the best ways is to focus on the most important statistical law, namely the Coulomb flow. You must be very familiar with this part. You don't need the detailed explanation. But anyway, in an inertial range, the energy is transferred from small k region to large k region without being dissipated. Here, the energy spectrum obeys the famous Coulomb flow. And the inertial range is believed to be sustained by this kind of Richardson cascade process. Namely, the energy is injected into the large scale. Such kind of velocities should be broken up to smaller bands self-similarity, and eventually the energy is dissipated into some small scales. However, probably you know this is only based on an image. This is just a cartoon. Nobody has ever confirmed clearly. Why is it? This is because it's too difficult to identify each eddy in a classical fluid. So if quantum turbulence can be to be a simple model of turbulence, it should show some express the essence of turbulence. Based on this motivation, quantum turbulence studies have entered a new stage since the middle of 1990s. Up to now, there appear many important studies. Of course, I don't have enough time to explain the detail of each work. But for example, about the energy spectrum, experimental conformation of the chromophore spectra, or theoretical constellation of, at finite temperatures. But here, there is a very important question. What happens to quantum turbulence and the energy spectra at very, very low temperatures where the normal fluid component is negligible? Until up to now, there have been only 3 studies which directly study numerically the energy spectrum at 0 temperature. No direct experimental proofs. And the first contribution was made by the Paris group using the Gross-Pitaitsky model. The second is our group's contribution using the vortex filament model. The third is also our group contribution using the modified Gross-Pitaitsky model. Here I'd like to discuss the first one and the third one. So this is a Paris group contribution. By using the Gross-Pitaitsky model, they obtained a vortex tangle starting with from the Taylor-Green vortices like this. And they calculate the energy spectrum. But here you should know the Gross-Pitaitsky fluid is compressible. So in order to study the chromophore spectra, it's necessary to decompose the total energy into some components following the method used by the Paris group. This is the total energy of the Gross-Pitaitsky model, which is represented by the sum of the internal energy and the quantum energy and the kinetic energy. And the kinetic energy is furthermore divided into the compressive part with rotation free and the incompressive part with divergence free. The compressive part comes from the phonons or density waves, while the incompressive part, of course, comes from the quantized velocities. So this incompressive kinetic energy should obey the chromophore spectrum. So the Paris group calculate the energy spectrum of the incompressive kinetic energy. The right figure shows the energy spectra at a moment, and by using the linear fitting, they obtained the exponent nt as a function of time. The left figure shows the time development of the exponent nt, and certainly the exponent nt goes through 5/3 on the way of the dynamics. However, in the late stage, the exponent deviates from 5/3 because the sound waves resulting from vortex reconnection disturb the cascade process of the inertial range. But actually, several years ago, Professor Marc Brachet had a chance to visit me in Osaka. And in this case, I discussed many problems with him, but I asked him thoroughly why this exponent deviates from 5/3 in the late stage. And his comments is something like this. So in order to overcome these difficulties, we started this calculation. First, we solved the Gross-Pitaitsky equation in wave number space in order to use fast Fourier transformation. Second, we achieved steady state turbulence. Please remember this figure. In order to do that, we introduced a dissipate term that dissipates the high wave number Fourier components, namely the short wavelength phonons. Then we excite the system on a large scale by moving the random potential. What to do? So this is a normalized Gross-Pitaitsky equation in a real space, which is transferred to the Gross-Pitaitsky equation Fourier space. Here, the psi is a healing length corresponding to the vortex core size. To solve the Gross-Pitaitsky equation numerically with high accuracy, we use the Fourier spectral method in space with cubic periodic boundary conditions. So how to dissipate the energy at small scale? In this work, we introduce here phenomenologically the dissipation term gamma k, which is represented by such kind of step function, which means the dissipation operates only in the scale smaller than the coherence length psi. Later, this type of dissipation was justified by, for example, the coupled analysis of the Gross-Pitaitsky and the Borov-Dujan equations, which is discussed, for example, in this paper of ours. Anyway, how to inject the energy at large scales, which was done by moving random potential like this. But here, we let the random potential satisfy this type of space-time correlation. Here, the characteristic variable x0 determines the scale of the energy contained range. Anyway, by using such kind of method, we can excite the system at large scale x0 and dissipate energy at small scale xi. Now, we'd like to achieve the steady state turbulence. When the random potential starts to move, before long, some small vortex loops appears and gradually grows and develop to a vortex tangle like this. And this is a time development of each energy component, which is found to be increasing. And before long, we can obtain a statistical steady state. Of course, each quantized velocities are fluctuating, moving. But for example, the total length of the vortex cores becomes statistical steady. And each energy component is also becomes statistical steady. So by using this method, we could obtain the statistical steady state, which is sustained by the large-scale excitation and the small-scale dissipation. So once we obtain such kind of steady state, we can expect this kind of energy flux. This is the horizontal axis refers to the wave number. The upper part shows the energy flux in the incompressible kinetic energy. The lower part is the energy flux of the compressive kinetic energy. By moving the random potential, the energy is injected into the fluid here. The injected energy is transferred from small K region to large K region by the genuine Richardson cascade process of quantized velocities and eventually dissipated here. And of course, there may be some cascade process of phonons, probably this corresponding to the wave turbulence, but I don't explain the detail here. So in order to confirm this picture, we calculated the energy dissipation rate epsilon and the energy flux pi of the Richardson cascade process. So our most important concern is that whether pi is comparable to epsilon or not in the steady state. And how to calculate the energy dissipation rate? In the steady state, we turn off the large-scale excitation suddenly and monitor the time development of the energy. Thus, we obtained from the decay, in our case, epsilon is about 12.5, something like this. And the calculation of the energy flux pi is more just complicated, mathematically complicated, because we have to consider the energy budget equation in a Fourier space. But anyway, we could calculate the energy flux pi as a function of a wave number k, and this region corresponding to the inertial range. And the first point is pi is about constant in the inertial range. Next, pi is comparable to the energy dissipation rate epsilon we obtained in the last view. So we could confirm the picture of the inertial range as written in usual textbooks. So what happens to the energy spectrum? As we expected, the energy spectrum over the Coulomb flow, the black points refer to the numerically obtained spectrum. The black solid line refers to the Coulomb flow spectrum. Here is the excitation range. Here is the dissipation range. The inertial range wasn't so wide though, but anyway, we could obtain such kind of Coulomb flow spectrum. Actually, this is the first numerical confirmation of the Coulomb flow spectrum by the Gross-Pitaevsky model. So quantum turbulence was found to express the essence of classical turbulence. The inertial range is sustained by a genuine Richardson cascade process of quantized velocities. So we can say another Da Vinci Code is realized in quantum turbulence rather than classical turbulence.
What's the resolution of that simulation?
The calculation was 256 cubed and yes, something like this. However, the story is not so simple as discussed by Sergei Nazarenko in the last session. The energy scale and the cascade process depends strongly on the scale. In the relatively large scales, larger than the mean distance between velocities, the energy spectra obey the Coulomb flow and the energy is transferred by the Richardson cascade process. However, in the small scales, we believe that the energy is transferred by the Kelvin wave cascade process. And as discussed by Sergei Nazarenko, the classical quantum crossover, this part is very important, but this problem is not fixed, still controversial. So I don't explain the detail here. Now let me go to the final topics of the quantum turbulence in atomic Bose-Einstein condensation. So according to the long history of research into superfluid helium, we know there are two main cooperative phenomena of quantized vortices. One is a vortex array in a rotating case. The other is a vortex tangle in a turbulence case. However, how about the atomic Bose-Einstein condensation? Almost all studies were limited to vortex array. Actually, little or there are no research about in this box. So here, let me show you briefly the usual setup of atomic Bose-Einstein condensation. Atomic Bose-Einstein condensation is created by the optical technique, what we call the laser cooling, which is trapped by the magnetic or optical potential in a vacuum. And the experimentalists used the optical spoon, namely the oscillating laser beam, rotating the BC cloud along the rotation axis, in this case z-axis, and what happened, and observed what happened from the top. So several groups have succeeded in observing and making and observing the vortex lattice in a rotating Bose-Einstein condensation. They are all the experimental results, okay? This is a Paris group contribution. This is a Colorado Gira group's contribution. This is MIT's, this is Oxford's. And this is a numerical calculation of the vortex dynamics in the rotating Bose-Einstein condensation by solving the Gross-Pitaevsky model. After the rotation starts, the BC clouds becomes elliptic. The blue region corresponding to the vacuum region. BC becomes elliptic, exciting surface ripples, and some surface ripples enter the condensate, eventually forming a vortex lattices. Once more, after the rotation starts, the BC becomes elliptic, oscillating, exciting surface ripples, and some surface ripples enter the condensate, eventually forming a vortex lattice. Certainly, this calculation seems to be consistent with the Paris group's contribution. Then we should ask here, how is it possible to produce turbulence in a trapped BCs? The first problem is that we cannot apply any flow to this system. The second is, this is a finite size system. Can we make turbulence with a sufficient wide inertial range or not? About the second problem, we were optimistic from the beginning because please remember the last calculation. The coherence length wasn't much smaller than the system size. However, we could confirm the Kolmogorov law. The problem is the first one. But this is our idea, how to produce turbulence in trapped BCs. First, we trap the BC in a weak elliptic potential. Next, we rotate the system first around the z-axis, next first around the x-axis, next around the z-axis, something like this. Actually, this idea has been already used in classical turbulence for water by the Shigeo Kida's group. And this is their experimental results. And the left figure shows here is water in the center. And the water sample cell is subject to the rotation around the horizontal axis and the vertical axis. Okay, and this is a visualization of the flow in the case of one rotation. Certainly, the fluid is found to mimic the solid body rotation, but if we apply another rotation, the fluid becomes turbulent. Here, you may ask, these two rotations is represented by their sum, thus being equivalent to a single rotation. No, it isn't, because it's a precession. And we consider the case where the spinning and precessing rotation axes are perpendicular to each other. Hence, the two rotations do not commute, and thus cannot be represented by their single sum. Anyway, we applied this idea to atomic Bose-Einstein condensation. In the case of two rotations, something like this, this is the dynamics of a condensate density. This is a dynamics of quantized vortices. In the case of three rotations, this is condensate density dynamics. And we obtain the statistical steady state, and we calculate the energy spectrum. In the case of two precessions, the blue points are numerical result. And certainly the numerical result seems to be consistent with the power law. In this case, the power eta is 1.78. And in the case of three precessions, the power is 1.69, which is closer to 5/3. So probably this may be more isotropic turbulence. What can we learn from quantum turbulence of atomic Bose-Einstein condensation? First, we can control the transition to turbulence by changing the rotational frequency or interaction parameters. For example, let's consider this kind of phase diagram. This is a rotational frequency. We know what happens along each axis. Of course, along this axis, we know there appears a vortex array along the z-axis. And we know here appears a vortex array along the x-axis. And as showed you before, by combining two rotations, here appears a vortex angle. Then what happens to the transition, vortex lattice and vortex angle? So by changing the rotational frequency, for example, such kind of vortex lattice should melt, changing to a vortex angle like this. This is a very important problem. Next, we can visualize quantized velocities. We can consider the relation of real space cascade and the wave number space. Anyway, the most important characteristic of this system is we can visualize quantized velocities by using the optical technique. The third is changing the trapping potential or the rotational frequency leads to dimensional crossover, 2D, 3D, something like this. So by using the atomic Bose-Einstein condensation, we can obtain the very, very controllable turbulence system. So this is the last view graph. Let me summarize my talk. We discussed the recent interest of quantum turbulence. Quantum turbulence consists of quantized velocities, which are stable topological effects. Quantum turbulence may give a prototype of turbulence, much simpler than classical turbulence. So this is another Da Vinci code of 16th century, which has now developed to quantum turbulence of 21st century. Thank you very much for your attention.
A few questions? Yes.
I've done a lot of calculations myself of the energy transfer in classical turbulence calculations. And the point I want to make is that we see a scale-to-scale energy transfer in classical turbulence, just like you're seeing in your quantum turbulence. And in that sense, it's Richardson-like. But there's absolutely no reason why the mechanism that's producing that scale-to-scale transfer has to be the eddy breakup mechanism that Richardson first suggested, and then Feynman re-suggested for quantum turbulence. It could be something else. It could be the wave turbulence we've heard about today. It could be some other type of vortex interaction of the line that Tony Leonard talked about in the first talk. So,
well, probably this point is just different from the classical cases.
not necessarily.
Yes.
So what about intermittency corrections? So the standard turbulence, we know intermittency is there, and it's also universal. And here you showed your spectrum. It seems to be the scaling seems to be a little bit less than -5. So can you make any statement on intermittency?
Yes, that's a very important point. But I don't know the reason. But anyway, I don't know the. You're asking the energy spectrum is just smaller.
Well, I mean, in intermittency, you can also look at higher order structural functions and you see more, not only the energy spectrum, which is contaminated by bottleneck, but from higher order moments or from looking at small scale quantities, PDFs, you would grasp some idea on the strength of intermittency for quantum turbulence.
Yes, about the small scale, but actually our calculation, the space resolution of our calculation isn't enough. So in our case, for example, here. So in our case, for example, this region is very close to the space resolution. So in our case, the vortex line length, mean vortex spacing is very close to the scale. So we don't have
other tricks. I mean, in standard turbulence, all these tricks have been applied, extended self-similarity, and so on.
Yes.
So I mean, I'm sure you applied those tricks also to quantum turbulence.
Yes.
At the moment, he's not making a commitment, so let's go on to the next question. Okay.
Can we go back to your slides where you are making the kind of sketch where there was a cascade on the top and phonon emission? I mean, a little bit before. You were having a kind of before. Yeah,
Yes.
this one.
Yes.
Okay, this one. I think this is a kind of picture you are proposing to
Yes.
try to explain
Right.
things. Okay. I'm a little bit surprised myself, and here is my question. That the phonon, you said there is only very weak interaction between the quantized vortice and the phonon. Another, okay, and I want to push also the point of Bob that in our field we have the theory of Kolmogorov, but the cascade, the mechanical model we are pushing to try to explain the cascade is completely
Yes. Of course, the
tentative and probably wrong. In which case, your community could be actually very useful to our community to try to propose other kind of mechanism, because as you mentioned, you can see the vortex, what we call, measuring vorticity in classical turbulence is one of the, major difficulty. Though again, I'm back to my question, can you guarantee that there is no some strong interaction between
Yes, of
phonons?
course, it depends on the parameter. It depends on the parameter. So, for example, by tuning or changing the parameter in the gross Pitagorian model, we can change the interaction. So, of course, we can make the case of both strong interaction and the weak interaction. But in our case, we were interested in the Kolmogorov flow, so we made a case of the interaction, of weak interaction.
Okay. Perhaps we should